All right, HL physics or engineering physics for grade 12. These two problems are just a carryover of what we did last class with rotational equilibrium. I just wanted to give you two more solved problems just so we could perfect, I think, two of the harder problems that we faced. Okay, so the first problem that we're going to look at is the sign on the wall problem. And then the next problem we're going to look at is equilibrium with a ladder leaning against the wall, okay? And how would we go about solving or setting up the equations for this problem? Okay, starting with the sign of the wall, a 20 kilogram sign hangs from a 2-meter long beam that has a mass of 10 kilograms and is supported by a cable at an angle of 30 degrees as shown in the diagram. Determine the tension in the cable, okay? So, like all translational or all rotational equilibrium problems, we set up these two equilibria, translational equilibrium and a rotational equilibrium. Okay, so starting off with translational, I'm going to look at two different directions. You have a horizontal translational equilibrium and you have a vertical one. And in this case, I wouldn't have to even really go and solve my translational equilibrium, but it's worth practicing. If I was to take a look at the horizontal equilibrium, okay, the normal force acting there is going to be equal to the force of tension, the x component of the force of tension, the cable pulling on the end of that beam. Okay, so that could be an interesting thing to solve, but we're not going to need it. That's not something that's going to help us with this problem. All right, that would be important if they were asking what is the force of the wall against the beam, because I got to make sure that my pivot is going to be able to withstand that force. Okay, so let's get rid of those because we don't need it. All right, now the other translational equilibrium that would be here is the force that the cable is going to be lifting up in the y direction is going to be equal to the sum of the forces of the sign and the sum of the gravitational force of the beam. Okay, well, that's pretty cool. I mean, I could go about doing that and maybe simply solving for the force of tension of the cable, but I don't really want to do that. Okay, and something I've seen for a solution for this problem is without even using translational equilibrium, I can solve the problem just with rotational equilibrium alone. Okay, so just looking at the sum of the torques. Okay, so for rotational equilibrium, the sum of the torque is going to be equal to 0. Okay, so that means the torque counter is going to be equal to the torque clockwise. Okay, so what's the counterclockwise? The counterclockwise is going to be the component of force in that direction, okay, times the length of the beam. All right, so the component of the force times in this direction, the force of tension in that y component times the length of the beam. Okay, so I can create that as the force of tension in the cable times sine of 30 degrees, that's going to give me the y component of that force, times 2 meters. Now, why did I have to do that? Because remember, the torque is always the perpendicular component. So that force of tension is acting perpendicular on the moment arm, which is 2 meters long. Okay, now the clockwise, sorry, I kind of put myself in the corner here. The clockwise is going to be the force of gravity, or the weight of the sign. Okay, so this guy, and the weight of the sign is going to be around 200 newtons times 2 meters. Okay, that's the torque due to the sign, and the torque due to the weight of the beam is going to be, let's see, how much is that? 100 newtons times 1 meter. Okay, oop. Yeah, where'd I go? Okay, and then if I rearrange everything, so that would make this, the force of tension is going to be equal to 400 Newton meter plus 100 Newton meter divided by sine of 30 degrees times 2 meters. And your answer is going to be, the force of tension in that cable should theoretically be 500 newtons. Okay? That's the answer to that problem. So you can probably get that using a variety of ways. Okay, so we did that using rotational equilibrium. Next, the equilibrium with ladder leaning on the wall. Okay, here's a classic setup. You're always going to be faced with this problem in introductory level physics classes in university. So let's try to work it. Okay. The problem that I presented in the video last time was a little bit more complicated because I had a guy walking up the ladder, but let's simplify it. Let's not use that one. Let's just look at the ladder itself. Okay, so a 10-meter ladder with a weight of 300 newtons is leaning against a wall such that it makes a 50-degree angle of inclination. Assuming the ladder rests without slipping, calculate the frictional force exerted by the floor to prevent the ladder from slipping. So they want you to calculate the frictional force right over here. Okay, if that frictional force isn't enough, the ladder is going to slip and slide down the wall. Okay, so what would the minimum amount of frictional force need to be? So again, let's start by setting up a translational equilibrium that involves the frictional force. Well, the frictional force is going to be equal and opposite to that normal force in the horizontal direction. Okay, so the frictional force is equal to the normal force. Okay, that's my translational equilibrium. And then if I wanted to do something in y, but I'm not going to have to do it, okay, my r, this value over here, is going to be equal to the weight, okay, of the beam. So r and then the weight of the beam. So I could also write that in here if I wanted to. So that would be my horizontal translational equilibrium and my vertical. So remember, you're always creating equations so that you can substitute them in if you have to. And this one allows us to find an equation where I can get FF if I need to have N somewhere in this problem, okay? So now let's take a look at the clockwise torque. Okay, what's the clockwise torque? So clockwise is going in that direction. So that is going to be this dude here. So the weight of the ladder, I'm setting my pivot point here. That's going to be my pivot point. Okay, so then the clockwise torque is going to be the weight of the ladder. Okay, and I guess the counterclockwise torque would be the wall, pushing it in the opposite direction. Okay, so let's take a look at this. Remember that the applied force for torque, the applied force has to be in the perpendicular component. So what I like to do, and it's different than in many textbooks, but I just draw the line here. The perpendicular component of that ladder would be the length down over here. Okay, so that's a cosine function, right? So then the clockwise torque is going to be the weight of the ladder times cosine 50 degrees times the length of the ladder divided by 2. Okay? Do you understand why length of the ladder over 2? That's because that weight center of gravity is acting halfway across the ladder. So if the length of the ladder is 10 meters, okay, then that's going to be a 5-meter point. So that should be 5 meters. The weight of the ladder, 300 newtons times 5 over 2. Okay? Then my counterclockwise torque is going to be F. It's going to be the normal force over here times that perpendicular component. So how do I get that? That's right here. It's the same. Okay, so that's going to be sine. Okay, that's going to be sine of 50 degrees, but it's sine of 50 degrees times L, the entire length of the ladder. Okay, and then I can create an equilibrium by equating them. So the weight of the ladder times cos of 50 degrees times L over 2 is equal to N times sine of 50 degrees times L. Okay, once I have that, I can cancel out the L's. Okay, I don't even need the length of the ladder. And then I can say that N, that force that the wall is pushing on the ladder, using my translational equilibrium, N is equal to FF. All right, so I can solve for, if I solve for N, I'll get FF. That's what we're after, okay? So then if I rearranged everything, 300 newtons times cos 50 degrees, okay, over 2 times sine of 50 degrees is going to be equal to N, which is equal to the force of friction. And then if I did everything, I would find out that the force of friction on that let me just get my calculation. Is 126 newtons. Okay, and that's how we do both those problems. Okay, so that's just kind of the way we'd set that up. All right.